Hypothesis test, one proportion. We're going to do examples of a one and a two-tail test, and we're going to do the conclusion by the p-value method, and then we're going to show a calculator method to be able to do it. So here's a two-tail example first. A genetic experiment involving peas yielded one sample of offspring consisting of 418 green peas, 141 yellow peas. Use a 0.01 alpha significance level to test the claim that under the same circumstances, 23% of the offspring peas will be yellow. Alright, so that's what we're supposed to do. So we see a 23% that we're testing, and that's a proportion that's being tested. We don't see the words average or mean, so we know we're in a proportion. Also, we only see one proportion being tested, not the difference between two, so it's a one proportion test. And we see words like test a claim, 23% of peas will be yellow. That's a two-tailed test because we don't see any commitment to words like more than 23%, greater than, less than, or below. We're just testing whether it's equal. So our hypothesis setup here is that HO, the null hypothesis, is the proportion of offspring peas that will be yellow is 23%, 0.23, and the alternate, same wording, but not 0.23. All two-tailed tests that we're going to have in the class always have this design right here. The HO gets the equals, and the alternate has the not equals. So then you boil that down, your hypothesis setup down into a simple notation here. Null hypothesis, P is 0.23, and P is, for the alternate, is not 0.23. Draw your picture. It's an alpha equals 0.01 significance level that we're given, but it's a two-tail, so we have to split the alpha in half and put it into two tails, 0.005 here, 0.005 there, because the proportion could be greater in the right tail or less in the left tail. So this is your setup. Now what goes here is the hypothesized population proportion, 0.23. Because what's going to happen is that you're going to run this test. You're going to assume that the null hypothesis is correct, that it's 0.23. Then, if you get an outrageous result, then you're going to reject that assumption. So you're going to say the proportion's not 0.23. If you don't get an outrageous result, then you're going to say, we're going to fail to reject. So that's what it's set up. So all these hypotheses are set up the same way. You assume the null hypothesis is true and try to reject it. We also run a normality check to see if you can really even use the normal curve to fit this, and it's NP is greater than 5 and NQ has to be greater than 5, and by putting in the numbers we see those are verified. Now we're going to get the Z, and we're also going to get the area beyond it into the tail. Okay, so our Z is the P hat, the sample proportion, minus the hypothesized HO proportion, divided by square root of the P and the Q are both from the HO, the P is from the HO, Q is 1 minus the P, and the N is the sample size. So the total P's were 418 plus the 141 yellow is 559 total, so the N was 559. The P hat of the yellow, the proportion of the yellow were 141 over 559. I just want to take a look at that proportion and see what it looks like on the picture. 0.2522. So 0.2522, is it here or is it out there? We don't know. We have to keep going on. But it's definitely to the right. So now you calculate your Z, and it's recommended to put the original fraction in there so there's no round off error. Here's your design. In the TI, you're going to do it like this. Be careful about the parentheses. And then you get 1.2493. Then you round it off to 1.25 is your z, rounded off to 2. Now we're supposed to find the area beyond z to find out how hard it is to get a z value of 1.25. So you got your second vars, which is distribution, normal CDF, 1.25 to 10. That's out in the right tail. 10 is so far out in the right there's virtually no area out there. That's why I like to go and just put that number. But it could have been 100, it could be 20, it could be even 7 or something, but 10 is a nice number. So that's what I use to go out into the tail with. And the mean of the z-scores is 0, standard deviation is 1. So when you run that, you get 0.1056 area beyond a z-score of 125. And you put that back on the picture. Alright, so here's your 1.25z right here. That corresponds to an area beyond it in the tail of 0.1056. You see that puts the z not beyond the z critical. The z critical is right on the boundary of where the alpha over 2 in this case area was, which is only 0.005. So this area is much bigger, which puts our z not beyond the z critical. So we're going to fail to reject. Now when you name the p-value, what is actually the p-value for a two-tail test? They like to compare the p-value with the alpha level, not the alpha over 2. So comparing the alpha over 2, it was 0.1056 was the area out in the tail compared to 0.005, but that was alpha over 2 split. So they multiply it by 2 on both sides to get the comparison of the entire p-value on both tails compared to the entire alpha level. That's just the way they like to do it. So for a two-tail, you got to multiply by 2 with that area to get a 0.2112 to compare it to the alpha level, the whole alpha level of 0.01. And you can see it's greater. So I already said that the z 1.25 is not beyond the z critical, so that's what a fail to reject is like. So then we're going to state the inclusion. In the math, we have the fail to reject the null hypothesis because the p-value is greater than the alpha significance level. In terms of the story, what you always have to do, you want to say there is not sufficient evidence to warrant rejection of the claim that 23% of the offspring peas will be yellow. So it's a fail to reject. And then you put at the alpha equals 0.0 level, and you put your p-value so that a reader that's reading the results can see how strong of a fail to reject or a reject it might have been, and what the alpha level you were testing it at was. So this is just my editorial comment here. Fail to reject is a wimpy finding. We couldn't reject the 23%, but we also did not prove the proportion is 23%. Like it could have been 23.1%. Alright, so now we're going to do the same example, but with a one tail. So to do that, I wanted to get a certain outcome, so I changed this 141 yellow piece to a 90. And I put in this wording, use the 0.01 significance level to test the claim that under the same circumstances, less than 23% of the offspring peas will be yellow. So I threw in those key words, less than. So this time we see that there is a commitment to testing for less than or below. So it's, or it could have been above or greater than. So it's a one-tail test, and since it's less, we're testing in the left tail. Okay, left tail. There's a T in there. Okay, so now we're going to go on with our hypothesis setup. Null hypothesis, proportion of yellow peas is equal to 0.23. Always, the null hypothesis has the equal sign. Always, always, in all the different designs. HA, alternate. The same wording for this, but we're testing to see if it's less than 0.23. Less than. We do our normality check. NP is greater than 5, NQ is greater than 5. Puts the stuff on the picture. This time we're testing in the left tail. Here's your alpha rejection region. Your 0.23 is your hypothesized population proportion. And we're going to get our z and find the area beyond it in the tail. This time I changed that number to the 90, so it's 508. P-hat is 0.1772. Looking on the picture, this is 0.23. 1772 feels like it has a chance to be out in the rejection region below 0.23, but we'll see. So we put our z formula together here. We calculated being careful about our parentheses, preserving the accuracy of the original fraction, not rounding that off. And we get this outcome for the z, which we round off to 2 places at the end there, negative 2.83. Now we're going to find the area beyond that. This time we're in the left tail. So I'm going to do my normal CDF, going all the way to the end of the left tail. This negative 10 is not really at the end, but it's so far out to the left, there's hardly any area there. And going up to negative 2.83 to find the area in the left tail beyond negative 2.83. And you get your 0, 1. And that probability is 0.0023. Put it on the picture, always to verify you're doing the right thing. Here's your alpha 0.01 rejection region, corresponding to a z critical here, which we could find, but we're doing a p-value method of conclusion, so we don't need to define that. Z is negative 2.83 with an area out there of only 0.0023, which puts us inside the rejection region. Our z is beyond the z critical. Our area p-value is less than the 0.01. Okay, so the p-value for the one tail is the entire area there, because we're not dividing anything by 2 or anything, so we don't have to double it to compensate. So this area is less than 0.01, and that's the alpha. So in this case, the p-value was 0.0023. We see that z is beyond the z critical in the left tail. So always just keep repeating that stuff in your mind. So the conclusion, in the math, we reject the null hypothesis because the p-value is less than the alpha significance level. In other words, going by the assumption that the proportion really was 0.23 or 23% yellow peas, we got an outrageous result mathematically. So something's wrong. What's wrong? The statistics isn't wrong. It's the assumption of the 0.23. That's why we reject it. Okay, so in the story, there is sufficient evidence to support the claim that less than 23% of the offspring peas will be yellow. Okay, so you always tie it back into the story. And then for the scientist reading the journal article or wherever your result is in, it's at the alpha 0.01 significance level, p-value equals 0.0023. Then I wanted to show you the calculator methods. You can do a hypothesis test on the calculator. You go to the stat menu, arrow over to tests, arrow down to one proportion z-test, because that's what we did there. And then you fill in your numbers. Your hypothesized proportion was 0.23. You have 90 yellow peas out of the 508 there. And then you have your hypothesis, your alternate hypothesis was less than, so you put that. Then you go down to calculate, and it calculates it out for you. And there's your z value, your p value 0.0023. Your p hat was there. So it has your numbers, but you still have to reason out the conclusion and write it all out.